Hi everyone, this is Mr. Lee. In this video, we are going to go over how to solve projectile motion problems. Now, this video is strictly in variable form, just so that we can get a little bit more practice in with how to solve these for your FRQs and for the AP problems. But I'm ready to take this time right now to write down this problem down on a piece of paper, like the previous unit where everything was basically an elevator problem. Everything here is basically this problem, but adjusted one way or another. So we have an object that is launched from the ground at an angle of theta degrees with a velocity of v meters per second. And I want you to determine the following. A, the total time of flight. B, the total range of the object, assuming it lands on the same horizontal axis. C, the max height of the object. And D, the final velocity and direction, which is the angle of impact. Actually, I'm gonna switch around D and C in this video, and you'll see why. All right, let's begin. Okay, so the first thing that you should always do, and I highly encourage you to do this for this part of the unit, you should always sketch out the situation. So here's my object, and my object leaves the floor with a velocity that we're gonna call v. Then when we actually do practice problems, you're gonna have a number there. And it leaves the floor at an angle of theta. Now, here's the other important part. Make sure that you draw the path of the object. It goes like this, pew, right? And it lands somewhere here. Okay, so there's a couple of things that we see here that are important for in the context of the problem. One of the things are this part right here. That's the landing position. So we're going to call that XF. Okay, is another way to describe your range or how far it went. Up here, okay, let's choose one of your dots. We're going to call this max height. And your max height should be probably like halfway between your start and your finish. We're going to call this starting point right here, XO, and that is also your time initial. And wherever it lands, that is time final. And that time final is actually key for this entire thing. And I think that's all there is. Oh, one final thing, because this is a very popular problem for multiple choices, make sure you indicate that the ball is going in this direction at the end. We're actually going to solve for this, but the more you get into the habit of actually drawing that final velocity of the ball landing, it'll help you out in the future. So the important thing in here is while landing, it's still moving. Okay, and that arrow there is just a constant reminder. So every time you draw this problem, make sure you put that arrow there. It's a constant reminder that even though that the ball is landing, it is still moving. All right, with that out of the way, let's see what we can do next. So for part A is going to be looking for the total time. Now, whenever we solve these problems, it's very important that you create your kinematics table for the x and the y axes. So I'm going to do the x-axis first. I'm going to create the y-axis later. So we have our initial position, our final position, our initial velocity. I'm going to put a little subscript x there as a reminder that we're looking at the x velocity, our final x velocity, your acceleration, the x-axis, and the time. Now notice time does not have a subscript. And that's because time is universal for the x and the y direction. All right, now here's a couple of things. I'm going to do I'm going to call these the givens. So these are part of the variables that is usually not given to you in the problem, but it's one of those things where we assume. One of the things that we assume is that your starting position is 0 meters. And that's just because, well, whenever we measure something, it's usually at 0 meters. It's the beginning of the measurement. If you remember from the previous video, where we did the post-lab analysis, we discovered that the acceleration on the x-axis, as long as there is no air resistance, will always be 0 meters per second squared. Now I'm gonna put a little star there. This is one of those things where the more you do this, it'll just become like second nature. But until it becomes second nature, it's one of those things where you should commit to memory. So that makes your initial velocity and your final velocity, so these are the same. And that's because, and this is important, your acceleration is 0, and your acceleration is the change in velocity over time. So because there's no change in velocity, your initial and your final velocities are the same. Okay, so let's fill out the rest of the table based on the information that we're given. if this is our velocity and we have this angle here, what we want to figure out is the horizontal velocity component, which I just drew with the dotted line. We're going to call this Vx. And so Vx is equal to V cosine of theta. Cosine because it is the horizontal component, and that horizontal component is touching that angle. So I'm going to fill that in here. V cosine theta and V cosine theta. And remember that V is the actual launch velocity of the object. All right, next up, let's create one for the y-axis. Now, one of the important things I want you to realize, just like a lot of the previous problems or the previous units, it is the setup that's the most important part for all of these problems. And the setup is how you can get to the final answer. All right. Our y position for this problem, because we started off on the ground, we're going to make our y initial 0. Okay. Now there will be times where our y initial is not 0 if we are launching an object off of an elevated height. But for this one, it's going to be 0. So let's do this again. Our y final, because we also reach the floor, this will also be 0. Okay, because whenever we're measuring something vertically upwards, we start off from the floor and we go up. So your position 0 will be the floor. Okay, now we have the initial y and the final y. So back to our sketch over here. Let's do so much. All right. Now, if we take a look at this y component here, that is our v initial y. So our v initial y, it's opposite of the angle, and so we have v sine theta, with v being the launch velocity, or the initial launch velocity. So I'm going to write that as v sine theta. And here, we don't know the landing velocity, okay, so we're going to leave that blank, but the acceleration in the y direction. So once again, this is one of those things you should memorize. I'm going to write it in red. The acceleration in the y direction will be g. As a reminder, please write that down as down. Okay, we are accelerating downwards in the y-axis, and that's because if we were to draw a free body diagram mid-air, only the force of gravity exists on the ball, and if we do a net force formula, it'll look like this: mg ma. Therefore, your acceleration will always be g. Okay, and because for projectile motions, direction matters, I'm putting that down there as a reminder. When you plug it into your formula, it should represent that we are going downwards. And of course, we don't know the time. All right, now here's a couple of things that you should know about these problems. I would say probably 9 out of 10 times, you're going to use the y-axis to find time. Now, there are those rare occasions where you do have to use the x-axis. And if you were to ask me, Mr. Lee, how do we know which one to use? To be honest, you don't. You just have to see which table has most of the variables that are given to you. And from those variables, you have to use the kinematics formula in order to solve for time. But one of the reason why I put A first, the total time, is knowing how long it takes for the ball to travel is the key to unlocking everything else in this table. Okay. Now, the other reason why it's usually the y-axis that tells us the time is because we start the time, right? So if this is the object on the floor, when the object is launched upwards, okay, we start the time as soon as it leaves the floor. So t start when object leaves floor. Okay, and then our stopwatch is running, and then we stop the time when the object is landing. T stop when lands. Okay, so when the object leaves the floor, the object is going what we call upwards, and when it lands, it's when it's going downwards. And this is all of the y-axis, and that's why it's usually the y-axis that helps us determine the time. Okay, so now that we have the table set up, and we went over all the conceptual ideas, remember, we still have to find the total time. And so at this point, what we have to do is we have to use our kinematics table in order to, or our kinematics formula, in order to figure out the time. So have the kinematics formulas probably at the top of your paper, because we're going to be referencing it throughout. We have delta x is equal to v initial times time plus 1/2 at squared. V final is equal to V initial plus acceleration times time. V final squared is equal to V initial squared plus 2a, and then we have delta x right there. So those are the formulas that we will be using throughout this entire video. All right. Now, using those three formulas, okay, we have to use the process of elimination to see which formula we have to use in order to find time. Now, there's 2 out of the 3 that actually has time in it, which is the first 2. And so between the first 2, you have to just ask yourself, all right, what variables do I have? What variables do I not have? So the variable that we're looking for is time, so we don't have final velocity. So we can't use a formula with final velocity, which leaves us with the very first formula that we're going to use. All right, now it's important for us to always start off with the original formula. Remember, for the FRQs, you get all the points for the setup, okay? And part of the setup is identifying the correct formula. Now for here, we're only looking at the y-axis variables, so I'm just going to actually update this formula so that it reflects that. We're looking only in the y-axis. All right, and at this point, all we have to do is plug in the actual variables that we found. So our delta y, because we started off on the floor and we'll land on the floor, this is actually 0. Okay, our v initial y, we said that was v sine theta, okay, and we're looking for the time t, plus 1/2, that a is g, but because it's downwards, we're going to say negative g, t squared. The next line down, I'm just going to use this opportunity to just clean this up a little bit. V sine theta t, oops, that should be a negative 1/2 gt squared. Okay, so from this line here, we can get a little bit fancy. We're going to factor out a time variable here. So we get t is equal to, or t times v sine theta minus 1/2 g times t. And we're going to divide both sides by t. That way, we can actually eliminate t overall, because 0 divided by t gives us 0. So we get 0 is equal to v sine theta minus 1/2 gt. All right, so now we have that time variable that we're looking for. At this point, it's just algebra. So I'm going to move the 1/2 gt to the other side. Okay, I'm going to multiply both sides by 2. And then last step, I'm going to divide both sides by g. So 2v sine theta divided by g. All right, then when we're actually solving a problem, and I do have an example video here where we're doing everything in terms of numbers, you would have a final answer as your time. Okay, so at this moment, I am going to update my table for 2v sine theta divided by g as my time. All right, and let's do this in some blue. So 2v sine theta divided by g. 2v sine theta divided by g. And you'll notice I put the time for the both x and the y, and this is because time does not care about your your axes. Time is universal for the x and the y. All right, so that's how you solve for time. Now, what about v, max range? Okay, so luckily, we can use the same table. And the reason why we're going to use the same table is because the time that we just found was for total time. Okay, and max range is found by looking at the total time of travel. So we don't have to create a brand new chart. We can use the same chart again to find the total range. Okay. Now, range is in terms of x final. So you know what? I'm going to update my table there to represent that. This is my range. And we're going to do the same strategy. We're going to look at our kinematics equations, our 3 kinematic equations, and we see here that the first equation actually has our delta x in there, so we can use that to find your total range. All right, so I'm going to scroll down. There we go. So we can see that delta x is equal to v initial t plus 1/2 at squared. All right, I'm just going to update this so that it reflects our x variables. So we have xf minus xo, that's delta x, v initial x times t plus 1/2 ax t squared. So next line down, I'm going to make sure that I have my zeros in place, and my acceleration in the x-axis is actually 0. And so I'm going to say this is 0. Now it's important that you let the graders know that you knew that the acceleration in the x-axis is 0, and so actually show that math. So that leaves us with xf minus xo equals v initial x plus t. We said that our xo is 0 as well. So we say our final position, which is our range, is equal to v initial x. We said it was v cosine theta times the time that we just found. Okay, and so because that's a substitution there, I'm just going to put it in parentheses. We have 2v sine theta all divided by g. Okay, and we're going to multiply that out, and we end up with a total range of 2v squared times sine theta times cosine theta all divided by g. Now this is your answer in numerical form. However, when we're actually solving problems, we could just plug in the values there to actually find the answer. Now, I just want to do a quick little side note here. Okay, in the previous video for the post-lab analysis, one of the things that we discovered was that for your x-axis, there is no acceleration. So our position time graph for our lab looked like this. That's a generalized shape. So this shows that we have constant velocity. And this was all about Unit 1. And if you remember, from Unit 1, our big formula, a general math equation, was that velocity is equal to distance over time, or position over time. And that's what our formula turns out to be. If you look at this line here, you can rearrange it to see that with constant velocity, you can just use this formula instead for constant velocity only. Now, if that's a little too much to remember, it's okay. Just use the kinematics formula. It all works out. Okay. All right. So now that we have our final position, we are actually going to solve for D, which looks for your landing velocity and your landing speed. All right. So this is D here, and this is your landing velocity and direction. Now, this part of the video, I think is really cool because of the way that we're solving for things. Because we're solving for things in variable form, a lot of the things really cleaned up nicely. So that's one of the benefits of solving in variable form. For the landing velocity, there's two things that you need. You need v final x, which we already have, and v final y. All right, so if you, I guess we should update our table because we found it. Oh boy, that's a lot. 2v squared sine theta cosine theta over g. All right. So this is 2v squared sine theta cosine theta all over g. All right, so we just found that. Okay, so if you notice here, we basically have everything in the x table filled out, and the only thing that we have left is to find vfy. So let's find that first, okay? Because we need your final y velocity in order to find your landing speed. So in order to find this, we're going to use the kinematics table, and we need to find your final y velocity. If you look at this equation here, this equation actually has everything that we need for to find the final y velocity. So I'm just going to update it to represent that we are looking at the y-axis only, like so. Vfy is what we're looking for. We know that our v initial y, that is v sine theta, okay? And our acceleration in the y direction is the acceleration due to gravity, so negative g. And our time that we found, actually I forgot what it was. Let's take a look. Our time that we found was 2v sine theta over g. All right, so we have 2v sine theta all divided by g. And that is our final y velocity. Now, let's not leave it like that. Let's clean it up. We know that we have g in the numerator and g in the denominator. So those two will cancel out, leaving us with v sine theta minus 2v sine theta. All right, so here we have v sine theta minus 2v sine theta. And when we subtract the two, because there are like terms, we get negative v sine theta is equal to v final y. Now, this is really cool. This is a wow kind of moment because if we take a look here, this v sine theta, this negative v sine theta, is your initial y velocity, except that negative shows that this is going down. So the initial Vy is equal to your final Vy, but downwards. And this is pretty awesome. If you remember from the post-lab analysis video for the y versus t graph, we got something that looked like this. Okay, so what this means is that your initial slope right here is equal to your final slope right there. Your two velocities are the same. So your v initial y, which is the slope right there, is your v final y, which is your slope right there. But it's in the negative direction. Cool stuff. All right. So now that we have our v final y, now we can actually solve for your final landing velocity. So your final landing velocity, you need two things. You need vfx and vfy to find the actual landing velocity, v final. Okay, so at this point, we're going to use a lot of trig. Okay, so it's important that you understand the rules of trig to really see how we're going to find vfy. So vfx is the x component of the landing velocity, which goes forward like this. So that's vfx. Okay, and our vfy is like this, like so. That's vfy. Now, these two vectors are important because if we add the two vectors together, we have an object that's going right and an object that is going down. We know that our v final should represent this. So our v final is both going right and downwards. Now, for those of you with the keen eye, you can see here that if we rearrange all of the vectors, what we actually get is a triangle. And let me show you where we can see the triangle. So here we have vfx, and we have our vfy right here. And so if we connect the very start of vfx and the ending of vfy, we get a right triangle, like so. Okay, where right here, this is our angle, and this is the direction or the theta that we're looking for. So with right triangles, what we need to do is we need to use the Pythagorean theorem to find the actual VF. So let's set up our formula. We can say VF squared is equal to VFX squared plus VFY squared. Okay, so that's the Pythagorean theorem. But if we actually are looking for VF, we see that it's the square root of VFX squared plus VFY squared. Now, we didn't come all this way here to leave it in those terms. So, and my next line down, I'm going to actually fill it all in. We found that our VFX is V cosine theta squared, and our VFY is negative V sine theta squared. Okay, and so what we get is V squared cosine theta squared plus V squared. So that should be sine theta squared. Okay, so at this point we can do a little bit of fancy algebra, right? Let's take out that v squared, and then we get, I'm going to rewrite it as sine theta squared plus cosine theta squared. And for those of you that remember your math identities, this is very unique and this is very special. This is equal to just 1. And so what we get is v squared times 1. And if we are square rooting a square, what we end up with is just v. Whoa, this is really cool. So what you're telling me is that your final landing velocity is equal to your initial launch. And the answer is true. Okay, now, so this should make sense because our horizontal velocity doesn't change and our vertical velocity, the vertical speed itself, doesn't change. It's just a direction. So if both of those components are the same, that means your initial launch velocity and your final landing velocity, it has to be the same, except for the direction. Okay, so this is a big moment. This is really cool. It's a huge aha moment for us. Okay, so it's the same as launch. Okay, so what about theta? So theta, we're going to use trig again. So we're going to try to find that angle theta. Now, hopefully, at this point, you're realizing, okay, so if I know my VFX is the same, if I know VFY is the same, except it's going downward, and I know my VF is the same, that must mean my theta, my launch theta, is the same. And you'd be right, but I just want to prove it to you. And you should know the proof too, in case you have to solve it in the future. So we're going to use the trig identity. We're going to use tangent theta, which is equal to opposite over hypotenuse. And our opposite, according to our triangle above, our opposite of this angle here is VFY. So VFY divided by VFX. I'm going to put a negative in front of that VFY, just as a reminder that it is negative. You'll see that in the next line down. And here we have negative V sine theta all over V cosine theta is equal to tangent theta. And so V divided by V, that gives us 1. So we get negative tangent theta. All right, so that must mean that your theta there is your theta in there. But if we were dealing with numbers, you need to actually find the angle. So to find the angle that is hidden within our final answer right there, you have to take the inverse trig function. So it will be tangent inverse tangent of negative tangent theta, and this will give you simply theta. Yeah, but the negative theta. There we go. So our direction would be the angle that we launched off of. So when it's landing on the floor, it's landing at the same angle that it left the floor, except a big difference. We launched going up and to the right. This angle here will give us down and right. And that's that. That is how you solve any and all projectile motion problems when we're going full range. So there's one more. For this one, we can't use our final time, and this is to find max height. So what I'm going to show you is I'm just going to show you how to set up the table for max height, because we'll get plenty of practice in. Max height. There's a couple of important things for the table for the max height. Okay. So I'm just quickly jotting down the tables. All right. So YO, YF, VY, VFY, A sub Y, and T. All right. So here's our table. Now the big difference here is one, our total range will change because now it's half the range or half the total range. Okay, so that'll be different, but everything else is the same as from before. Our acceleration will still be 0. Okay, our initial position will still be 0. Our initial velocity will still be v cosine theta. Our final velocity will still be v cosine theta. But our time, this right here, is the big difference. Now, if we were to go back to our original drawing, right there, we said the max height occurs at the halfway point of travel. So if it occurs at halfway through the entire time of travel, our time we can actually update to be a half of the total time. So I'm going to write that there. So our time is equal to 1/2 total time. So for example, if your total time of travel took 20 seconds at the max height, we will find everything in terms of 10 seconds because that's half of the total time. And the rest of the formula or rest of the table would almost be identical. Okay, let me show you the big changes. So our our initial y position is still 0. Our y final is what you're looking for. That's your max height. Our v initial is still v sine theta, but this is the big point right here, our v final y. Okay. Now, before I just show you what our v final y is, I want to go back to our previous units. I think this is like unit 2, where we looked at the position time graph for the y-axis. Okay, so we know that when we leave or when we launch off of the floor, okay, we start off at a y position 0, it goes up, and then we land back at y position 0. Okay, and I have to pointed out that your slope in the beginning and your slope at the end, it's the same except for direction. And so from here, let's go to a Vy times time graph. So if this is a Vy times time graph, in the beginning, we start off with a positive velocity. And at the end, we end with a negative velocity. And the important thing is that this slope is equal to negative g, or negative 10. And so if we're looking at the halfway point right there, that's the key to filling out our table. At exactly halfway, our y velocity is 0. I'll put that in red because that is a big update. Okay, at the peak, we're not moving up or down in the y direction. However, we are moving side to side, so there still is speed. But in the y direction, there is no velocity. Okay, and our acceleration in the y direction is still g. I'm going to write it down. Okay, and then you would just use your kinematics table to find the actual max height. And that, ladies and gentlemen, is how you solve almost all the problems for this unit. I'll see you next time.